Hello class, welcome to section 14.3. We'll be focusing this time on events with and probabilities, and then conditional probability as well. Whereas last time we talked about events with or probabilities, those were questions that revolve around union. So the probability of this or this is a union question, whereas the probability of this and this is referred to as an intersection question. So a few definitions. We talk about independent events, which are events that have no effect on one another. For example, flipping coins. And when they have no effect on each other, or when their probabilities are easily calculable, we can use this simple equation. The probability of this and this, or for intersection, is the probability of the first event times the probability of the second event, when they go in that order. Dependent events affect the way we set up the problem, meaning that when one event has effect on the other, for example, without replacement. When I flip coins, when I flip a coin twice, whatever I got the first time doesn't affect what I get the second time. They're completely independent of one another. But let's say, for example, I'm drawing cards from a deck. A standard deck has 52 cards. Now let's say I want to draw a red card. Now half the deck is red, so that's 26 out of 52. So I have a 26 out of 52 chance the first time I draw a card. Now if I don't replace it, that means I don't put it back in the deck after drawing it out, I now have 51 cards. So drawing two cards from a deck without replacement are considered, each draw is considered a dependent event. One affects the other. Of course, I'm reducing my sample space from 52 to 51, but even beyond that, if I drew a red card the first time, I now have 25 red cards left versus 26, and so on and so forth. So that's the idea of the dependent event. And conditional probability, the other part of this section, is where we talk about two events, one of which has already happened. So the probability of event B happening, provided that another event A has already occurred. Read probability of B given A. And you can see the way it's written here that is significant. When I write it, whatever events happened first, in this case my A, should be in the second position in that writing. So again, it's read the probability of B given A. And we'll look at the definition here in a little bit. First, let's look at some examples of intersection before we get to conditional probability. Again, anytime we have the word and, like we said here, what's the probability of rolling a 3, then rolling a 4? So 3 and 4 is the way we'd interpret that. And since these are happening, one after the other, we'll say, well, what's the probability of rolling a 3? What's the probability of rolling a 4? 1/6 for each one, so 1/6 times 1/6 gives me 1 out of 36. What's the probability of having 3 boys in a row? Same idea. The probability of boy, boy, boy. Again, we can generally assume that the having a boy does not affect the chances of having another boy. We'd say, well, the probability each time is 1/2. So 1/2 times 1/2 times 1/2 gives me 1/8. An experiment involves flipping a coin twice, then rolling a die. What is the probability of getting 2 tails and a 4? So again, these are all independent events, so let's look at each one individually. The probability each time of getting tails is 1/2. Probability of getting a 4 is 1 out of 6. So when you multiply it all together, you get 1 out of 24. The probability of a particular team winning a championship in a given year is 3 out of 65. What's the probability this team wins 2 years in a row? So again, the probability of any particular year is 3 out of 65. Then it's not, neither one's dependent on the other, so we can just simply say 3 out of 65 times 3 out of 65 gives me 9 over 42/25. What's the probability of drawing 2 kings from a standard playing card deck without replacement? Now this is a good example of when we can use a tree diagram to help illustrate the possibilities that we have. Now normally, like we did before, we said, well, probably the first time of drawing a king is 4 out of 52. There are 4 kings in a standard deck. Now if I haven't replaced it, so I took the card out, there's now 51 cards left over, and only 3 kings left over, assuming I got a king the first time. So that's why my second probability is 3 out of 51, because it's now changed. These are dependent events. So my probability is 12 out of 2652. Now a tree diagram, as you can see here, helps to visualize it. So each time, the first time I can draw a king, or I can get not a king, that's what my N stands for. King, of course, is 4 out of 52. Then the chances of not drawing king are 48 out of 52. That's the first event. The second event is drawing again, so I could draw a king. So the top tier, let me illustrate. So we're talking about drawing 2 kings, so the first time, that should be straighter, is this path. Now the second time drawing king puts me right here, which means there's 3 kings left out of 51 total. So when I find the probability, I multiply those 2 fractions together. And the same goes for anything else. So for example, let's say that I said, what's the probability of drawing 2 cards? The first is which is a king, the second is not. So again, if I said, what's the probability of drawing a king the first time and not a king the second time? Well, I said the first time, if I draw a king, I get a 4 out of 52 chance. If I do not draw a king the second time, I go this way. And I have a 48 out of 51 chance now of getting my not king. So to find the overall probability, I would multiply those 2 fractions together. 4 out of 52 times 48 out of 51, and the resulting fraction would of course be my probability. And this is an example of how tree diagrams can be used to help illustrate these problems. And I'll go over another one later on. Again, the probability of getting a king and an ace. Again, and means intersection. First time through, 4 out of 52. Second time through, 4 out of 51. 4 kings, 4 aces, so you get 16 out of 2652. Now, conditional probability. Again, the event A has already happened. The probability of event B, which is dependent, is this. So, that is the probability of the intersection of B and A divided by the probability of A. Or if you're looking at the number of elements in a certain event, the number of elements in the intersection divided by the number of elements in A is another way of phrasing it. Typical example, what is the probability of being dealt a heart if the card you've been given is red? Using our formula. So, and notice the way this is phrased, as opposed to the ones we just did. We've been told specifically the one you've been given is red. So we've been told that one of the condition has already been met, that we have a red card. As opposed to saying, first we do this, then we do this. We've already said, you've already been dealt this card. What is now the probability of getting this other one? So since the red card's already happened, I've already been dealt that, or it's almost like drawing, R goes in the second position, then my heart, H, goes first. And it's equal to the probability of the intersection of H and R divided by the probability of R. So in this case, the probability of a heart and a red card. So in other words, is there an intersection between the two of them? And in terms of a deck of cards, we can simply say it's going to be well, there are 4 suits in a deck of cards, 13 for each suit. Hearts are, you have of course 13 hearts. How many of those are red? Well, all of them. So 13 out of 52 is our probability. And like I said, you could also think of it as how many elements are in B intersection A. So how many elements are in hearts and red cards? That's 13. The probability of R, drawing a red card, is again 26 out of 52. Or if you're looking at the number of elements in R is 26. And when you do the math, you'll end up with 13 over 26, or 1/2. Now this one comes from the book. And if you want to follow along, it's on page 694, number 53 through 55. Suppose a softball player has a 300 batting average, meaning that, and that's where it's making a kind of a simple assumption, that there's a 30% probability of her getting a hit each time at bat. Assume the player bats 4 times. What is the probability of her getting a hit? And we'll actually add in only a hit in her first at bat. So out of all 4, she just gets a hit in 1, and that being the very first one. B, what is the probability of her getting 1 hit for all at bats? And C, what's the probability of her getting exactly 2 hits? So this is an example, like I said before, where a diagram comes in fairly handy. And now I know it's better when you can see everything that's large on your screen, but to get everything in, I'm going to have to zoom out. So what's the probability of her getting only a hit? And let me correct my grammar. At least correct somewhat. I'm sure that's not perfect. You English majors who are watching this and probably criticizing me. So here's my diagram. So if now my H represents getting a hit, of course my M represents getting a miss or not a hit. Obviously if there's a 30% chance she gets a hit, then there's a 7% chance that she doesn't get a hit. So each time, each one of these represents an at-bat. So I have 1, 2, 3, 4 tiers. So the first question is, what's the probability of her getting only a hit at her first bat? So at her first bat, so what we're going to do is just follow the path. Especially when we're considering more than one event happening in succession. So if I take she gets her first hit at bat, or first and only hit, in her first at bat. That means I'm going this path. That means she missed every other time. So well, that's going this way, here, and here. I'm highlighting each branch that represents what happens at the at bat. First at bat she gets a hit. The last 3 she misses. So like before, just like with the intersection, we'll multiply each of the probabilities along the way. 0.3 times 0.7 times 0.7 times 0.7. 0.3 times 0.7, 7 times 0.7. So that means she has a 10% chance, approximately, of getting only 1 hit over all 4 bats, and that hit coming on the very first try. Now part 2 is similar, but it says, what's the probability of her getting 1 hit for all at-bats? Meaning that this is a broader question. So that means, again, we're figuring out for all of her at-bats, she only has 1 hit to show for it. But we're not specifying when it happens. The first question was specifying that 1 hit can only happen the very first time at bat. And there's really only one way for that to happen. The second question is, what is the probability she gets 1 hit altogether? But that 1 hit can come at any time. So like I said, it's a broader category that we're looking at. So let's find out how many of those situations there are. Well, that's the first one we found. And let me see how well I can write this. That was 0.1029. So let's find any other instances where she just gets one hit. Well, there's not too much more I can do up above on this top part of this graph, because if I go any other path, I'm going to have more than one hit. So I'm going to start down here now. So let's say she misses the first time, but then gets a hit, but then misses the last two times, because again, she's only getting one hit. It takes me down this path. And again, I'm going to multiply the same values. Now, if you notice, it's the same overall values. There's 1.3 and there's 3.7s. So when I multiply, I'll get the same number, 0.1029. Let's find another one. Well, she still get a miss the first time. Let's say she gets a miss the second time. But then she gets a hit, but then she has to miss again. So once again, 3 misses, 1 hit. The same numbers are being multiplied, so we know it's going to come out to be 1029. Hopefully you can see that. I know it's kind of neon green. And lastly, again, I'm just going down the possibilities. She could do 1 miss, 2 misses, 3 misses, which means her last one's a hit. Same numbers, so again, 0.1029. So now when we're talking about all of them, we have to consider all of these as possibilities, which means we need to add them all up. That means we're considering each chance. There are 4 possible ways she can get one hit over in all 4 bats. So we need to add up all the probabilities. So we're saying 0.1029 times 4, which means there's about a 41% chance she gets one hit, irregardless of the way she gets it, in all 4 bats. So overall, when you're not specifying when that hit occurs, she has about a 41% chance of getting only one hit out of all 4 at-bats. And lastly, what's the probability of her getting exactly 2 hits? Same idea. We need to figure out how many ways can she get exactly 2 hits. Well, one way, of course, is she just gets 2 hits right off the bat. No pun intended. And it gives me 0.3 times 0.7 times 0.7. Or another way would be she gets 1 hit, then misses, gets another hit, and then misses. Again, exactly 2 hits. Or gets a hit, misses, and then gets a hit. There again, exactly 2 hits. So I found 3 paths already for getting that number of hits. So before I continue, I want you to see if you can find any remaining paths. So put me on pause and then come back. Now if you try, you should have a total of 6 paths that you can find. So there should be 3 others that are down here. Now I'm going to repeat some colors, so bear with me. Again, 2 hits. So I could say miss, miss, hit, hit. I could say miss, hit, miss, hit. Or I could say miss, hit, hit, and then miss again. And you should see something of a pattern here. You can see some symmetry in the way I'm drawing these lines. So there are 6 total ways. Now that means each time, and again with this, each time you're multiplying 2.3s and 2.7s. So let's see what that is. So 0.3 times 0.3 times 0.7 times 0.7. That means each time I have 4% chance of getting that particular combination. Now it happens 6 times, so say times 6. So I have 26% chance, or this person has a 26% chance of getting exactly 2 hits in all 4 of her at-bats. Again, this is another example, one of the more common examples you'll see of, or common ways of utilizing a tree diagram to help illustrate these problems. So this concludes section 14.3. As always, if you have any questions, feel free to contact me, and have a good day.